is the term that's typically used to describe when a lens's angle of view changes with its focus position. The term, as best as I can tell, comes from the cinematic world where focus in a dialogue scene is pulled back and forth between the speaking characters as they speak. This results in a rhythmic change in framing, if the lens is susceptible to this, that would make it look as though the scene or the camera was breathing in and out. What's up, everybody? I'm Jason, and welcome back to the channel. Now, breathing was not something that I ever thought about as a still photographer. However, since I have started shooting video, it's become something that I have to at least consider when looking at lenses. That said, while I've become more aware of the effect over the last several years, I've never really deeply understood what was going on and how it behaved. And combining that with the, as we'll see in this video, somewhat flawed way that most reviews go about demonstrating and discussing breathing, well, that led me to some misconceptions of what was going on and ultimately really misconceptions about how good or bad lenses could potentially be. Now, that said, this phenomena is absolutely understood by optical engineers and lens designers. However, engineering is always a matter of cost versus benefit, and the problem now is that the technology is shifting, and with it are requirements as well. Now, historically, lenses have either been intended for motion, picture, or still applications. Video and cinema lenses are almost always designed to compensate for breathing because it is a factor that affects good-looking video. However, doing that increases their complexity and, along with it, their costs. Now, on the other hand, because breathing isn't an issue for still photography, it's never been high on the engineer's priorities to address, and it's kept the cost of our lenses down as well. However, today, hybrid and entry-level cinema cameras are changing things. Hybrid cameras like the R5 and Sony Alphas have made video a major focal point on what would have traditionally been a still camera, and with still camera lenses, or what would traditionally have been still camera lenses. And on the other hand, entry-level cinema cameras like Canon's C70 and C300s, and even C500 for that matter, also have started using still format lenses to provide more functionality, better accessibility, and to maintain lower total costs compared to their higher-end cinema PL lens counterparts. As a result, for many of us, breathing is now something that we really should be considering when we look at reviews and lenses. And we have certainly seen that reviewers have taken note of this. For example, Brian over at The Digital Picture has absolutely started including breathing tests in his reviews. However, for me, this is where the problem starts to arise. The traditional way to demonstrate this aberration is either a full focus range pull in a video type review, or two images, one shot at the minimum focus distance and one shot at infinity. Now, unfortunately, these tests and the reviewers that are doing them often don't explain everything or even really offer much additional commentary beyond that simple demonstration. And it's not hard. I did it to assume that this full range test is somehow reflective of the performance of the lens in a more reasonable or traditional use case where you're only pulling focus over some fraction of that lens's focus range. So before we can start trying to talk about how to interpret test results or how we should be testing things, we really need to start understanding the behavior of breathing in more detail. As I said, most reviews, at least the text ones, demonstrate breathing with two pictures. One shot at the minimum focus distance and one shot at infinity focus. And to be honest, the same really ends up being true for a video review, even though they'll show a full focus or a full focus pull from those 2 points. That's the extent of how they show it. However, this poses an often unasked question, which is, how does that angle of view shift relate to focus position? That is, if we look at the two extremes, does that tell us anything useful about the middle or at some reasonable working distance? So the first thing I wanted to look into in this video and this series of tests was that. For whatever reason, I have assumed that this would be linear. That is, you would see the same change in angle of view if you move the focus closer by, say, a foot when the camera was focused at 20 feet or at 3 feet. Now, it turns out this isn't actually the case. So this is a graph looking at the angle of view shift versus focusing distance for my Canon RF 28-70 f2L USM at 28 millimeters. Now, even with a logarithmic scale for the x-axis, which is focusing distance, the plot is still a curve. And this means that we are dealing with an inverse exponential relationship here, not just a logarithmic one. Put another way, the angle of view shift is going to be exponentially larger the smaller, the closer the focusing distance gets to the camera. In fact, we can linearize this relationship, but we have to plot the image distance, or basically how much the lens's elements have to move to focus, against the change in angle of view. Now, aside from having a graph that's closer to a line, I don't think this actually provides as much useful information in practice, so I'm going to just ignore these. But this does throw a wrench in that traditional way of showing breathing. A lens may perform acceptably at normal working distances, but can appear to perform poorly because of how close its focusing or close focusing capabilities can be. And in fact, I have an example of this phenomenon. These are the performance graphs for a Canon 50mm f1.8 lens on the left and an EF 50mm f1.8 STM lens on the right. Now, if we just look at the maximum breathing for these two lenses, the FD lens's 9% beats the EF lens's 21% hands down. However, if I overlay the data on the same graph so that they both are on the same distance scale, we see these two lenses perform virtually identically over the shared focusing range. That extra 11% in the breathing seen on the EF lens happens entirely between the FD lens's 2 foot or 0.6 meter minimum focus distance and the EF lens's not all that much shorter 14-inch or 0.35 meter minimum focusing distance. Something else that's interesting and at least worth spending a moment on is talking about the direction the angle of view shifts and how that relates to the lens's design. Overall linear extending lenses like these 50mm primes move the entire lens away from the sensor to focus closer. Since these lenses don't have complex independent focusing mechanisms, they should all at least breathe in the same direction. And that should be tighter as the lens gets closer. That is, since the lens moves further away from the sensor, the image distance increases and therefore the effective focal length. So any lens that uses an overall extending design should see its angle of view narrow as they are focused closer to the camera. However, most lenses that we use these days are internal focusing designs, and these lenses move a few elements internally, and not the entire lens as a whole. And of course, on top of that, the complexity here can be compounded when a zoom lens is in question, with more things moving. Here's also where I found something else interesting. The direction of the angle of view change depends entirely on the design of the specific lens in question. So I looked at 3 of the lenses that I tested throughout the course of this test. A Canon RF 15-35 f2.8 LIS USM, a Canon RF 24-70 f2.8 LIS USM, and a Canon RF 28-70 f2L USM. Now for each of these lenses, I tested them all at their marked focal lengths on the zoom ring, and then plotted the curve for each of these lenses. I found they all had completely different behaviors in terms of what they did in breathing. For the 28-70, every focal length resulted in the angle of view widening as the lens was focused towards the minimum focus distance. But for the 24-70, the wide-angle positions of 24 and 35 millimeters actually saw that same widening of angle of view shift, but the longer focal lengths at 50 and 70 millimeters saw the angle of view narrow instead. Finally, in the case of the RF 15-35, while all of the tests resulted in the angle of view widening, the order of these curves wasn't the same. That is, on both the 28 to 70 and 24 to 70, while the magnitude of each curve changed, they stayed in order of focal length. So if 28 was the widest, and 35 would be next, and 50 and 70, and so on. However, with the 15 to 35, the 20 millimeter position showed significantly more shift than the other positions on that lens, including the two that flanked it, the 15 and 24 millimeter settings. So that is an interesting observation, but it also, all of this goes to what we can actually talk about or understand if we're trying to compare lenses, which is, it's really hard to compare lenses. Now, at this point, we've seen some data. The question you may be asking is, how did I get it? And what do you need to do the same if you wanted to look at your lenses? Well, this is actually pretty straightforward. The test target for this is very simple. It's nothing more than 2 squares of white gaffer tape on a black photographic background. They should be placed roughly in line horizontally, but don't have to be perfect. Moreover, there is no set distance that you have to put them apart, because that's not how I'm doing the test. I'm not measuring a single test. I'm actually making a comparative measurement. In fact, for longer lenses, you will probably need to put them closer to minimize the need for needing a huge working distance and therefore room or structure to work in. Now, the camera side of the test requires a tripod, and that's really it. Place your camera on the tripod and roughly level it, then adjust the height so that the two targets are roughly in line with the vertical center of the frame. Now, for each test run, I move the camera so that the white targets are near the edges of the frame. However, they should be in from the edge far enough that the bokeh from them doesn't get cut off when they're out of focus and fall out of the edges of the frame. Now, for my test runs, I used Canon's focus bracketing function to have the camera drive from close focus, the minimum close focus distance, to infinity in a number of steps. I set my camera up to shoot small JPEGs, since that would provide enough resolution for the tests and not so much that it bogged down the computer processing it. Shooting RAWs is not useful here, since the added dynamic range doesn't actually help. Now, you could shoot larger JPEGs, as the added size would help with accuracy to a small percent, but it will also increase the processing time, and quite honestly, in my testing, the change didn't contribute all that much. Now, the magic to all of this is in the processing. And for this, I wrote a custom Python script that uses OpenCV, which is a machine vision library, to locate the centers of the white targets and then calculate the distance between them. This is done for every file in that focus bracketing sequence. And then, since the last file is at infinity focus, and therefore the true focal length of the lens is what you were measuring there, I can compare each of the measured distances from all of the closer focus positions with that infinity focus position to see how much they're changing. Now, that said, there are some limitations in this whole process. For starters, for autofocus lenses, I'm getting the focusing distance from each image's metadata. Now, some cameras and lenses don't include this, in which case that's kind of a problem. And even when they do, like on my Canon EOS R5, the information is likely not 100% accurate. In fact, you may have noticed in some of my graphs, there's sort of a stair-step-like effect. This is a product of multiple frames being shot at each different real focus position, so the camera is moving the lens, but the files having the same metadata in their focus position information. Now, additionally, at least for Canon cameras, there are 3 different values that can be used to get the focus position, and they all differ. There is a focus distance upper and a focus distance lower metadata field, as well as a depth of field entry that has both near and far depth of field limits. Now, doing some digging, I have not been able to find a consensus as to what the upper and lower focus distances actually are. For these tests, I just averaged them together in my script, but that honestly might not be the ideal solution either. I suspect they might have something to do with flash distance calculations, which don't have to be precise, and therefore that would explain why these are not very precise as well. Now, you could also backdrive the depth of field equations using the provided depth of field and hyperfocal distance values, though these values also don't update perfectly with or precisely with every focus movement either. Now for manual focus lenses, I just test at the focus distances marked on the lens and then make a note of those and feed that into the software. Now one final note here is whether to do these tests stopped down or wide open. Now, in theory, you should get the same results in both modes, I think, but in practice, bokeh doesn't always get distributed uniformly around the point that's creating it, and there could be other aberrations at play. I ended up doing all my tests with the lenses either at f2.8 or f4, whatever was widest open for the lens, or at 2.8 in the case of the 28 to 70 f2. However, I did do a test run at f22, and the results showed slightly less shift than what I was measuring wide open. That said, I don't have a great answer here. This is an area that warrants more investigation. Now, well, having a better technical understanding of how all of this behaves is great. It also doesn't tackle the perceptual part of the problem, the perceptual side of the problem. And to be completely honest, I don't have answers to a lot of what I'm going to talk about here. This is not here's what you need to know. In fact, this is more of this is where I think we need to start looking. So this is definitely a topic for more research and discussion. Now, fundamentally, the problem with breathing is that it can become a distraction in video, not that it necessarily will. Now, if you are only pulling focus once in a given scene or in one direction, then breathing may not be an issue for you at all. Likewise, if you're making fast, frequent focus shifts, then breathing can become a much bigger issue. And as we've seen, how much a lens breathes and therefore how much of an issue it could be depends significantly on what focus distance you're using. Are you at 10 plus feet or 2 plus feet? That said, the first question we have to at least acknowledge is how distracting breathing is, well, actually may just be personal. And I don't see an easy way to put a threshold number on this. In the subsequent videos that I looked at specific lenses, I used a 2% change just arbitrarily. But as I said, that was completely arbitrary. I did not have any research to back that up. That may still be too much, or maybe more than is actually needed, and I don't have an answer for that yet. On a very real level, of course, I'd personally like my lenses to not have any shift in angle of view when focusing at all. But at the same time, the reality right now is that every lens I own has some amount of focus or angle of view shift, and they do the job that I need for them just fine. So how important is being perfectly zero? However, even if you're in that camp, the same camp as I, the no focus shift camp, consider this. To start with, breathing is really only an issue in certain situations. When you have a repeated full focus pull of some distance between two subjects from a locked off camera with a background that shows or exaggerates those changes. If you never pull focus or only ever pull focus once in a scene, that focus pull is done while moving the camera, or you shoot on solidly even lit backgrounds, which, okay, that's a bit niche. Breathing isn't going to be obvious at all. Simultaneously, even if you're in a situation where breathing could be a problem, consider that there are other optical aberrations that can be equally distracting. For example, if you're shooting with a fast lens for shallow depth of field, or just because you need the ability to capture that much light, background bokeh can change when focusing. Moreover, this will happen with every lens, regardless of how much or little it breathes, and can be absolutely just as distracting. So with that said, let me wrap this up here. The short of it, at least as I currently see it, is that the current way breathing is covered and discussed in reviews is, I'm going to say, problematic at best. Just presenting the minimum and infinity focus positions and that composition that has doesn't tell us anywhere near enough about how a lens behaves in the middle of that range, where we're most likely to be using it and most likely to be seeing problems with it. Moreover, even video breathing tests, at least the ones that cover an entire focus or the entire focusing range of the lens, suffer from the same problem. You see the maximum and the minimum, but you don't understand how things are playing out in the middle. Now, of course, as much as reviews are useful, absolutely do read them, follow them, use as many as you can when making buying decisions. In the end, the reality is no reviewer can test everything in enough detail to totally satisfy everybody's requirements. Ultimately, at some point, you have to take the plunge, buy a lens, and really test it for yourself. Now, that said, I am going to be publishing a set of videos looking specifically at breathing on a variety of Canon lenses that I have access to in the coming weeks. Additionally, after I get my test code cleaned up, I intend to make it available through the Points and Focus GitHub repository, so if you are interested in it, let me know in the comments below and you can test your lenses and maybe we could actually get something interesting going with it. Now, with that said, I am going to wrap this up here. I will be happy to try and answer any questions that I can in the comments below. If you found this video interesting or at least informative, let me know by hitting that like button. If this kind of thing seems like it might be your kind of thing, please consider subscribing if you aren't already. Finally, if you'd like to support this video and future videos like it, please consider hitting that thanks button if you can, or buying yourself something you've always wanted using the affiliate links in the description below. And, as always, thanks for watching, and I'll see you next time.